Welcome to The Debate. When you picture the origin of life, you probably imagine this boiling, chaotic, primordial soup.
Right, like a lucky lightning strike hitting a puddle.
Exactly. Random molecules just crashing into each other for millions of years until suddenly something sticks.
It's the standard textbook image.
It really is. It's a deeply entrenched picture of how we came to be. Highly continuous, extremely messy, and, fundamentally accidental.
Yeah.
But what if life didn't start as a random chemical accident? What if it started as a strict mathematical computation, operating on ancient rocks like a microscopic circuit board?
Which is a wild shift in perspective.
It absolutely is, and that is the exact premise of the material we are looking at today. It's a paper titled Abiogenesis as Contextual Token Realization.
Catchy title.
Very. It proposes a Gibsonian formalization of the origin of life, relying on discrete token physics and, advanced topological mathematics.
Specifically, W-Topos theory.
Right. And I argue that this computation-first framework correctly identifies abiogenesis not as a fluke, but as a rigorous mathematical emergence. One driven by precise, discrete rules on catalytic mineral substrates.
And I contend that while the mathematical formalization they use, the W-Topos theory, is undeniably elegant, imposing a strict binary, discrete computational ontology oversimplifies things.
You think it loses the biology?
I think by forcing this into a computational model, we lose sight of the continuously underdetermined and, inherently messy thermodynamic nature of prebiotic chemistry, which is actually what makes evolution possible in the first place.
Well, to really understand this computation-first perspective, we have to fundamentally reorient how we view physical reality at the microscopic level. Let's unpack that term, a Gibsonian formalization.
Please do, because it's usually a psychology term.
Exactly. In psychology, a Gibsonian affordance is about what the environment allows an organism to do, like a chair affords sitting.
Right.
In this paper, the environment, a porous mineral lattice on the early Earth, physically affords very specific chemical computations. The framework calls this process Recursive Token Lattice Synthesis, or RTLS.
RTLS.
Yes. It asserts that early life is absolutely not mere chemistry that got lucky. It is a structured process happening on a discrete catalytic substrate.
Let me just jump in here, because when you say discrete catalytic substrate, for the listeners, we are basically talking about a rock with very tiny holes in it.
Exactly. If you're trying to visualize a discrete token on a mineral lattice, just picture a rocky seabed where every microscopic groove in the rock is like a tiny cup.
Okay.
On this substrate, we have what the paper calls the local prebiotic state object. For any chemistry to advance toward life in one of those microscopic cups, it requires 5 very specific physical components to be present.
Right, the token conditions.
Yes. It needs chemical occupancy, meaning the right raw molecules are there. It needs energy. It needs a physical boundary, like the walls of the pore.
Sure.
It needs information, a sequence. And it needs the mineral catalytic state, meaning the rock itself has to be capable of accelerating the reaction.
Which all sounds perfectly reasonable when you describe it as a physical location, but the paper doesn't just treat these as physical ingredients.
No, it treats them as computational tokens.
Exactly. And that's where I have a problem.
But they function like tokens. Here is the mechanism that changes everything. Life, or proto-life, only advances when these local components achieve what the paper defines as a full complement.
Meaning all 5 are there.
Right. That means all 5 local token conditions are jointly and simultaneously met. If they aren't perfectly aligned, the system does not advance. It is mathematically gated.
Yeah, gated being the key word there.
This is what shifts abiogenesis from being a random accident in a continuum to a lawful computation. It's not just a soup where things drift together. The cup in the rock either has the full complement and the computation moves forward, or it doesn't.
But chemistry doesn't care about perfect zeros and ones. Defining chemical reactions as a strict computational process where a token complement is either exactly 0 or exactly 1 creates a highly artificial mathematical boundary.
I don't see it as artificial.
Chemistry is a spectrum of interactions. Furthermore, the text's own equations for local evolution include external forcing terms.
Yes. Thermodynamic drivers.
Right, we are talking about continuous ultraviolet radiation, thermal cycling, the ebb and flow of tides in a wet-dry cycle. These aren't discrete ticks on a clock.
But they trigger discrete events.
When you take a continuous thermodynamic physical process, like the slow warming of a rock under the sun, and you force it into a discrete computational framework, you abstract away the critical partial gradients that actually drive the physical transition from non-living to proto-living matter.
The binary nature of the model is precisely what gives it explanatory power over the chaotic soup model, though.
How so?
Let's look at the chemical full complement rule physically. Think about a computational logic gate, specifically a transistor and a microchip.
Okay, a transistor.
A transistor doesn't kind of flip. It requires a precise voltage threshold to flip from a 0 to a 1. I see the chemical full complement rule operating exactly the same way in these microscopic mineral pores.
But a pore isn't a transistor.
Not perfectly, no, but a prebiotic polymerization event, like linking two amino acids together, or the stabilization of a fat molecule to form a vesicle boundary, that only advances when all the local steric and energetic compatibilities physically aligned.
Sure, you need the right conditions.
You need the monomer, the energy, and the mineral alignment simultaneously. It doesn't just occur by a vague partial chance. It is a discrete physical gate that either opens or stays closed based on local conditions.
I'm sorry, but a transistor is engineered by humans in a sterile clean room to behave perfectly. Early Earth was a constantly fluctuating, dirty environment.
It was messy, yes.
You can't expect microscopic mineral pores to act like flawless silicon chips. And the paper's own definition of metabolic throughput contradicts this clean binary.
In what way?
In defining the functional observables for proto-life, metabolic throughput explicitly requires sustained gradient use. Sustained gradients are, by definition, continuous phenomena.
At a macro level, yes.
Think of a thermodynamic hill, heat slowly dissipating, or protons flowing across a gradient. How on earth can a strict, stepwise recursive math equation natively account for the inherently continuous nature of a sustained thermodynamic gradient?
It accounts for it by...
The mathematical equation dictating local evolution here moves in discrete ticks of time. State at time t plus 1 equals state at time t plus the tokens. That is a mathematical map mistaking itself for the physical territory.
I disagree.
The territory is a continuous chemical flow.
I see why you think that, but the tension you are highlighting between discrete steps and sustained gradients is actually resolved beautifully when we look at how macro-level continuities emerge from micro-level discrete events.
Okay, explain that.
What looks like a continuous sustained gradient at the macroscopic observational level, like looking at a whole hydrothermal vent, is actually the aggregated result of countless discrete token transfers at the micro level inside the rock.
Aggregation doesn't erase the continuity, though.
Think of water flowing over a waterfall. It looks perfectly continuous to the human eye, right?
Yes.
But physically, it is fundamentally composed of discrete, quantized water molecules moving in specific states. The framework isn't mistaking the map for the territory. It is providing a higher resolution map that reveals the territory is actually pixelated at its most fundamental chemical scale.
Pixelated?
Yes. The continuous gradient is just an illusion of scale.
I understand the waterfall analogy, but a waterfall is a bulk phenomenon. Abiogenesis is not.
Why not? They're both physical processes.
Because abiogenesis requires incredibly specific, highly idiosyncratic macromolecules to form and interact. The pixels in this case aren't uniform water molecules. They are incredibly complex chemical environments.
Which the token conditions account for.
But a mineral lattice has defects. It has overlapping catalytic domains. It has wild thermal fluctuations that do not neatly resolve into a single binary step function. If you filter out all that noise to make the math work, you lose the very dynamics that allow novel chemistry to occur.
Okay, if we accept that these events are happening in isolated, pixelated mineral pores, your next logical question has to be, how on earth do you get millions of these isolated, pixelated events to coordinate into a globally living cell?
Right, the big jump.
And the paper provides an answer. The text introduces something truly profound here. It's called the protocell emergence theorem.
Yes, the theorem.
It argues that life isn't a mystical discontinuity where soup suddenly wakes up. Instead, it is a gluing event in W-Topos theory.
W-Topos theory being the topological math they use to stitch these local states together.
Right. Topos theory maps how local spaces connect to form a global reality. Imagine a quilt.
Okay.
Each patch of the quilt is one of those microscopic cups in the rock. For a global living system to emerge, 4 functional pillars must lawfully stabilize across neighboring patches of the catalytic lattice.
And those are?
Those pillars are boundary persistence, metabolic throughput, informational heredity, and recursive reproduction. When these 4 pillars satisfy their local thresholds and perfectly agree on their overlaps.
Perfect agreement.
Yes. When the boundary from pore A connects seamlessly with the metabolism in pore B, they mathematically glue together into a unique global W-sheaf. This predicts that life emerges in threshold-like bursts of complexity, rather than through smooth, linear accumulation.
A phase transition.
Exactly. It's a literal phase transition, from chemistry to biology.
Okay, let's talk about what happens when it doesn't glue perfectly. Because I am really not sold on the strictness of this admissibility class.
It has to be strict to be functional.
The W-sheaf gluing law demands that local sections agree perfectly on overlaps to form this unique global state. But in the paper's abiogenetic realizability classifier, they include what they call an underdetermined state.
Right.
They define this as a state where partial prebiotic functionality appears, but closure across the 4 pillars is incomplete.
Yes, it's a state where the computation hasn't fully resolved.
But let's translate that into physical reality. An underdetermined state isn't just a math error.
I didn't say it was an error.
On early Earth, this might look like a lipid membrane that forms perfectly, and it even traps some energy inside, but it completely lacks the RNA information to copy itself.
Which means it's not alive.
But it's a beautifully constructed engine with no steering wheel. It's partial. It's messy. My argument is that if local sections must agree perfectly to be classified as admissible by this mathematical theorem, this mathematical idealism fails to capture the chaotic networks of early Earth.
I don't think it fails to capture it. It just...
Early Earth was nothing but underdetermined states. By categorizing a partial cell merely as an underdetermined or failed computation, the framework dismisses the very crucible of evolution. Life is a sloppy, underdetermined process that constantly remodels itself.
But
forcing it into a W-Topos gluing event where everything must perfectly agree seems like a theoretical physicist's dream imposed on a biologist's reality.
Defining something as mathematically underdetermined does not dismiss its physical reality. It just rigorously categorizes its systemic status. The framework doesn't deny that the sloppy, chaotic crucible exists.
It certainly downplays it.
It just states that the sloppy crucible is not yet life. The underdetermined states are the search space. They are the mineral lattice trying out billions of different token configurations.
Trying out.
What the protocell emergence theorem states is that true proto-life, a system capable of sustained heredity and metabolism, only arrives when that local agreement is actually reached. The sheaf gluing isn't an arbitrary physicist's demand. Think about what a cell actually is. A cell is a space where the boundary, the metabolism, and the information do in fact perfectly coordinate to survive.
Perfect is a strong word in biology.
If the boundary is stable and energy is flowing, but it can't replicate its genetic code, it dies. It doesn't glue. It falls back into being an underdetermined chemical slurry. The math perfectly describes the biological stakes.
But treating those partial states merely as a search space implies a teleological drive, like a computer program trying to compile code until it gets it right.
That's just a metaphor.
But chemistry isn't trying to compile into a cell. It's just reacting to thermodynamics. And when we look at the experimental implications of this theory, this computation-first idea really starts to show its cracks.
I completely disagree. How do we actually test this? That is exactly where this theory moves from abstract mathematics to physical laboratory reality. Our NTLS is a testable framework.
Is it?
Yes! Section 11 of the paper outlines how we can physically construct mineral lattices with molecule-scale bit sites. We can pulse these microscopic sites with thermal or electrical forcing and monitor them in real time.
Right.
We can look for persistent sequences and what the authors call lattice-coded error patterns. We can actually watch the W-field calculus play out on a laboratory bench.
Right. And here's exactly where the framework reveals its own physical limitations. I want to zero in on a very specific detail in that experimental proposal.
Which one?
The text suggests that researchers can optionally seed with minimal ribozymic structures if the spontaneous search stalls.
Well, as an experimental accelerator, yes.
Wait, hold on. You're talking about dropping a highly evolved biological molecule into the mix. A ribozyme is an RNA molecule capable of acting as an enzyme.
I know what a ribozyme is.
It is an incredibly advanced piece of biological machinery. If the Gibsonian framework's lawful token closure is inherently sufficient to cross the threshold into life, if the discrete computation naturally drives the system toward these bursts of complexity, why would an experimenter ever need to inject a biological cheat code like a ribozyme when the search stalls?
It's not a cheat code.
Is it the very suggestion of using it concede that computation-first minerals simply aren't enough without the messy, continuous, advanced biological chemistry that this framework claims to supersede?
No, that is a fundamental misinterpretation of why the seeding is proposed.
How else can you interpret it?
To understand it, we need to look at the lattice propagation law, specifically how it uses the graph Laplacian.
Okay, the graph Laplacian.
And just to explain that for our listeners, the graph Laplacian is essentially a mathematical map. In this context, it models the neighborhood of the rock. It maps exactly how a chemical state in one tiny pore of the mineral lattice physically influences the pore right next to it.
Sure, mapping the overlaps.
Exactly. But the sheer size of the configuration space for possible chemical combinations across that entire neighborhood is astronomically huge. Seeding the experiment with a minimal ribozyme does not invalidate the fundamental rules of the computation.
It certainly short-circuits them.
What it does is artificially place the system further along a computationally valid pathway. Think of it like placing a chess piece mid-game to test the endgame algorithms.
Okay, I see the chess analogy, but
It just accelerates the process so human researchers can observe the W-sheaf gluing event within a human lifetime, rather than waiting a million years for the spontaneous search to cover that massive phase space.
if you place a chess piece mid-game, you're no longer studying the opening moves.
You're studying the mechanics of the rules.
By dropping a ribozyme onto a mineral lattice, you are studying ribozyme chemistry. You are not studying abiogenesis from scratch. The entire point of origin of life research is figuring out the opening moves.
And the framework gives us the rules for those opening moves.
The framework claims that RTLS is the mechanism of abiogenesis. But if RTLS stalls in the lab without biological intervention, then the mathematical formalism hasn't actually solved the physical problem of how non-living matter crosses the threshold.
It absolutely has.
It has just built a highly sophisticated mathematical simulation of the process, one that requires physical reality to be artificially accelerated and neatly discretized to even function.
But the framework itself acknowledges that the physical substrate dictates the evolution. The external thermodynamic forcing and the physical geometry of the pores are what dictate the search.
Then let this search happen without biological seeds.
What the mathematical formalism provides us is the precise metric for what success looks like. Success isn't just generating one persistent molecule. It is the joint stabilization of all four functional pillars. A true, measurable gluing event.
I just think it's too neat. Too tidy for early Earth.
By formalizing abiogenesis through W-Topos theory and contextual token realizability, we are finally rescuing the origin of life from the realm of the passive random soup.
Rescuing might be a bit strong.
We are offered a rigorous, testable ontology where structure and computation necessarily precede biology. The rock computes the cell.
Well, I will happily grant that treating early chemical environments, like mineral lattices, as sophisticated information processing substrates is a massive and necessary leap forward.
Glad we agree on that.
Is infinitely superior to traditional models of continuum chemistry that rely entirely on chance encounters in a vast open ocean.
Exactly.
But while the discrete token physics framework is a beautiful mathematical induction, I maintain that life's origins ultimately reside in the messy, continuous, underdetermined chemistry.
The sloppy crucible.
Yes, that thermodynamic messiness resists being perfectly glued into strict local to global mathematical sections.
Well, we both agree, at the very least, that recognizing the computational capacity of the physical environment fundamentally changes the paradigm of origin of life research.
Absolutely.
The transition from chemistry to biology is an information problem just as much as it is a thermodynamic one.
I agree entirely. Whether it operates via strict binary logic gates in a pore or through chaotic, overlapping chemical gradients, the mineral lattice itself is acting as an engine of complexity.
Crossing the proto-life threshold remains one of the most complex, arguably the most profound puzzles in all of science. The Gibsonian framework provides a fascinating new lens, but it leaves us to explore the physical realities and the topological mathematics themselves to make a final judgment.
The models and equations are just waiting for the experimental data to either validate them on the lab bench or, force them back to the drawing board.
So the next time you find yourself looking at a piece of porous, ancient rock, you have to ask yourself, is that just a dead stone? Or are you looking at a stalled computer, just waiting for its full chemical complement?